Hey guys, this is a review of Units 1 and 2. Okay, Unit 1, we learned quadratics. It was kind of a review about grade 10 math, and we added a few extra things. So we talked about key features of parabolas. So we reviewed how to find the roots of a parabola, which we learned a couple ways, factoring or the quadratic formula. We learned about, depending on what form of a quadratic, it might be easier to use one method versus another. So in order to factor and use the quadratic formula, standard form is the best, ax squared plus bx plus c. So it's nice to have an equation in standard form. If it's factorable, we could factor it and then set each bracket equal to 0 and find our x-intercepts. Or we can quadratic formula it. We also talked about, really quickly, if something was in vertex form, just isolating x in order to find the roots. So like subtracting k from both sides, dividing by a, square rooting. So that kind of thing, just isolating x. And if it's in factored form, obviously, super easy to find the roots. Okay, we also talked about finding the vertex. So completing the square was something you learned in grade 10. And that's that method where you put it into vertex form from standard form. We also learned about partial factoring, which is where you take an equation that's in standard form. You set the y coordinate equal to c. So whatever the y-intercept is, that's what you set y equal to. And you end up with an equation that looks like, say, 9 equals, I don't know, 3x squared plus 6 or whatever it is. Plus 9. And then the 9s end up canceling out. So you end up with 0, this guy goes away, and then you end up just being able to factor and find your x's, and then you find the middle of that in order to find the vertex. And we talked about finding y-intercept by setting x equal to 0. Okay. We also talked about graphing, so just being able to graph an equation from vertex form. We just talked about the different forms of a quadratic, standard, factored, and vertex form. We did some word problems. We did linear quadratic intersection and writing equations of quadratics given roots and a point or vertex and a point or some information. And that was Unit 1. Unit 2 summary was a tricky one. You got a cue card for this guy. So if you're doing a retest, you can still have a little cue card for this. You had to identify if it's a function or not. You had to be able to use function notation and understand what it means. Figure out the domain and range of any function. Graph parent functions and transformations. So these are all the parent functions that we talked about. And then we talked about transforming it when we add in an A, a K, a D, and a C. And that was Unit 2. So let's just go over a few review questions. Feel free to skip through this video quickly or pause it or whatever you need to do. Okay, so factoring. You want to be able to factor not just for this course, but for every other math course you'll ever take in your life. Factoring is good. So here's a little quick factoring tree. I always like to check for a common factor first. So are these divisible by anything? They sure are. They are both divisible by 2. So right away, I would always common factor first if I could. So I'm going to factor out a 2, and I'll be left with x squared minus 25. Common factoring is just like dividing both terms by the same number. Okay, after I check for that, then I just look at what it looks like. So if it looks like this, let's say it has a couple of terms separated by a minus sign, and both are perfect squares, like so I can square root them, then I know it's a difference of squares. If it's got 3 terms, like x squared, some kind of number, x plus a number, like this, it's a trinomial. And it's either simple, like this guy is, or it's complex, like this one is, because it has a number in front of the x squared. Okay, so let's just finish these 3 examples. So the first question, 2x squared minus 50, I common factored it, and now I can see inside the brackets, it is a difference of squares. So I can factor that into 2 brackets, and I just square root each term, so that becomes x. Square root of 25 is 5, and one's a plus and one's a minus. Simple trinomial. I'm looking for 2 numbers that multiply to 18 and add to 3. I guess they multiply to negative 18. And I'm just going to pop them right into my brackets. So I'm going to start with x. I know that 6 and 3 multiply to 18. And if I make it negative 3 and positive 6, it's going to add up to positive 3. Duh, so that's done. This guy, there's a couple methods: Australian, decomposition, guessing, chart method. So whatever you do, here's decomp. I'm going to multiply the 2 and the 15. So I'm looking for 2 numbers that multiply to 30, and then I want them to add to 11. So I know right away it's 5 and 6, but if I'm not sure, I can make a list of things that multiply to 30. Once I know my numbers, I replace my middle term with those 2 numbers. So 2x squared plus 6x plus 5x plus 15. It doesn't matter the order of these two. Any order works. Then I'm going to chop it in half and common factor each half. So I can see that these guys are both divisible by 2x. What do I have left from this guy? Just an x. What do I have left from this? A positive 3. Okay, then I'm going to carry this sign down. So plus. What are 5x and 15 divisible by? 5. What's left from my first term? X. What's left from my second term? Positive 3. These brackets will always be the same, so I'm going to common factor them out. So I just end up with x plus 3, and then this 2x plus 5. So that's factoring. Definitely be comfortable with factoring. Guaranteed that'll be something you need to know. Okay, finding roots, vertex, and y-intercept. Let's just go through this. There's so many different strategies, and I can't possibly show you all of them in a short video. But yeah, let's just do some stuff. Okay, roots. I think I would try to factor if I can, because I really don't like the quadratic formula personally. So I can see that they're all divisible by 2, so that's what I'm going to do. And then I'm going to see if I can factor it. Okay, so I divided them all by 2, and I can see that 6 times 2 would make 12, and 6 plus 2 is 8. So I'm going to factor it one more step farther. I'm going to turn that into a trinomial. And it will be x plus 2, or 6, and x plus 2. So now it's really easy for me to find the roots. Once an equation's in factored form, I can just set each bracket equal to 0. Because really when I'm finding roots, I'm setting y equal to 0. And then I just isolate x. So here x is negative 6, and in this one x is negative 2. So I've got 2 roots. Okay, if I want to find the vertex, let's do that next. I'm going to show you completing the square, but that's not what I would actually do here. I would actually, I know my x-intercepts are negative 6 and negative 2. So I would find the halfway point between them. So I know my vertex is going to be halfway between 2 and 6. So it's going to be at negative 4. I know it's going to be there because my vertex is right in the middle of my parabola. And then I would just sub negative 4 back into this original equation in order to find y. But I wanted to show you completing the square in case you forget it. So just really quickly, completing the square involves factoring out an a from the first 2 terms, like that. Next step, I want to turn the bracket into a perfect square trinomial. So I'm going to make it x squared plus 8x plus 16. And I got the 16 by doing 8 divided by 2, so that's 4, and then squaring it, so that's 16. And I can't just add a 16, that's crazy. So I also have to subtract a 16, just so I don't change my actual equation. My next step, I'm going to pull the negative 16 out of the bracket, and I'm going to make it a negative 32 because it has to get multiplied by that a value out front, since everything got divided by 2 when we put in the bracket. So I end up with that. Feel free to skip any steps here. I'm just showing all mine. Now I'm going to factor this bracket, and I know how it's going to factor. It's going to factor into x plus 4 squared because it's a perfect square trinomial. So 2 numbers that multiply to 16 and add to 8 are 4 times 4, 4 plus 4. And then I'm just going to do negative 32 plus 24. which is going to be -8. So I can see that my vertex is -4, -8. And I got that by completing the square. But as you can see, I could have got it a lot faster by using this, -4, and then subbing it back into my equation. So -4 squared plus 16 times -4 plus 24. I could have got also y equals -8 going that route too. And that's a lot faster. So if you know the roots, why take all the time to complete the square? Okay. What else? Oh, y-intercept. So to find the y-intercept, you can just set x equal to 0. So that's the definition of the y-intercept. Or I can just tell right away, if it's in standard form, I know my y-intercept is going to be 24. So there you go. All right, moving on. A quadratic function has roots at 4 and -6, and it passes through that point. So to show you quickly, it's telling me it has roots. So right away, I'm going to factored form. Factored form looks like this. I'm going to use R and S as my factors. So that's, as soon as I see the word roots, I know factored form is going to be the best strategy here. And now I'm going to sub in stuff that I know. So my points here, 2 and 8, that stands for x and y. So I'm going to sub 8 in for y. I don't know a. And I'm going to sub 2 in for x. Then my roots are at 4 and -6. So I know when I want them to go into the brackets, I have to sub them in opposite. So I have to put -4 and +6. The reason being, if I put x minus 4 and x plus 6 in factored form, I know that when I like pull them out of the brackets to find the roots, that's going to give me a root of 4 and a root of -6. So something to keep in mind when you're subbing them back into your equation. And now I'm just going to solve for a. So I got -2 times 8, which is -16. I'm going to divide both sides by -16. So I can see that a is going to equal -1/2, just to simplify 8 over 16. So a equals -1/2. And I just need to sub that back into my original equation. So I got y equals -1/2 x minus 4 and x plus 6. So this guy right here is my final answer. And if it wants me to put it in standard form, you should be comfortable with that. That's just foiling this and then multiplying everything by -1/2 afterwards. Okay, linear quadratic intersections. That's where we have a linear equation and a quadratic, and we're trying to find out where they intersect. So I'm going to sub them into each other. They're isolated for y, so I'm going to sub their y values into each other. So x squared minus 2x minus 8 equals 3x minus 4. Then I'm going to toss everything to one side. I'm going to move it all over to the left. So I'll get x squared minus 2x minus 3x minus 8 plus 4 equals 0. And just collecting my like terms, I'll get x squared minus 5x minus 4 equals 0. My next step would be, is this factorable? So things that multiply to -4 would be, say, -4 positive 1, -2 positive 2. Like, they're not going to, I can't factor this. So that's too bad. If I can't factor it, factoring would be my number one choice. If you can't factor it, then you got a quadratic formula. Because you're trying to figure out what x equals. You're trying to find the points of intersection. So I'll have to quadratic formula this, which I'm not going to do. It takes too long. So, I mean, really, I'll just show you what it would look like. So if I'm quadratic formulating this, I have -b, so that would be 5, plus or minus the square root of b squared minus 4ac. And then the whole thing is divided by 2a. And then you would get two different answers potentially, or one, or none. So if you get nothing, if there's a negative under the square root, then it means these two things don't intersect, which is a possibility. So if you get a negative under the square root, then there are no points of intersection. If you get a positive number, then there are 2 points of intersection, and you should find out what they both are. So you'll get 2 values for x. Once you get those 2 values for x, whatever they are, you'll need to sub them back into either equation in order to figure out what y equals. I usually pick the linear because it just seems easier. So you'll get 2 y values, and those will be your 2 points of intersection. If you just get 0 under the root sign, then that'll give you 1 point of intersection. So 1 value for x. Whoops, not 0. I don't know what it is. And then you'll sub that back in for your 1 point of intersection. There's a video on this, though, if you need some more help with it. Okay, word problems. Again, we're not going to do it. We just don't have time in this video. But word problems are just uncovering, like, what are you trying to find? Usually it's the vertex, the roots, or the y-intercept. Or you're subbing in a value for x or y. So, you know, for example, you could have like a soccer ball. So somebody's kicking a soccer ball and it's making a quadratic relationship. And you could be trying to find out what's the maximum height of this soccer ball. So now you know if it's asking for max height, we're looking for the vertex. So that means we're going to complete the square or partial factor. And since it's looking for height, when we graph this soccer ball, the height is our y-axis. So usually we're looking for the y value of the vertex. And depending on what your variables are, sometimes the x-axis is time. So the time at the vertex would be like when the max height occurs. Sometimes you're looking for when would this soccer ball hit the ground after the person kicks it. So if you're looking for that, then, so like if you're looking for when does it hit the ground, then you're looking for a root. And you're looking for this root. So you would have to interpret the roots that you get when you solve this problem. If you're looking for something like initial height, what's the initial height of the ball? Then you're looking for the y-intercept. You're looking for where does the ball start on the ground. So you just got to interpret what the question's asking. And that's it for Unit 1. Unit 2. So functions versus relations. You should know what a function is and like be able to explain it in words. A function is when for every single value of x, there can be at most one y value. So let's just take x equals 2, for example. There is a y value. It looks like 2. But there's not more than one y value. What about when x equals 1? Yeah, there's one y value. What about when x equals negative 2? There is only one y value. So this is a function because for each of their x values, there's only one y. You can also tell it's a function by doing a vertical line test. But that's not really an explanation. That's just a strategy that helps us figure out if it's a function or not. This one would be just a relation. It's not a function. Because check out this, like, let's say negative 1. There's actually a y value here. It looks like almost 3. And there's a different y value here, like almost negative 1. So there's 2 different values. So that makes it not a function. And when we look at a table, as far as I can tell from this relation, it looks like a linear relationship, and I know that's a function. For every value of x, there's only one value of y. This guy, however, is a relation. I don't know what it is, but I can see that when x equals 1, it has 2 different values of y. Okay, function notation. This is when we replace y with something called f of x. It's just a more concise notation. So if something asks us to find f of negative 3, that means we want to know what is the y value when x is negative 3. Okay, so we just sub in a negative 3 for x, and we solve it. So this would be 9, and then negative 3 times negative 3 would be positive 9. So this would equal 18. So a statement that says f of negative 3 equals 18, this actually means when x is equal to negative 3, y is equal to 18. That's what that means. So you should be able to understand function notation. Graphing. This was the tricky part of Unit 2. So being able to identify the transformations is key and be able to graph them. Okay, so if we have a negative out front of the function, that is a reflection over the y-axis, over the x-axis. Whoops, sorry. Reflection in the x-axis. In order for it to be a reflection in the y, it would have to appear inside the function, so under that square root sign. So we know it's a reflection in the x, so instead of our graph going like this way, now our graph is going to go this way. It's going to be reflected over the x-axis. This right here, a +1 inside of the function is the root sign. So since that's under the root sign, we know that's going to be our left-right, our horizontal translation. So this guy's going to go left 1. It's always opposite of what you think inside. And then this -3 is outside of the function. So that's going to go down 3. So for this radical function, I like to figure out my starting point. So I'm going to go left 1, down 3. And then I know my graph is going to go like that. And I know just from graphing the parent function, let me graph the parent in blue here. It starts at 0, 0, then it goes over 1, up 1. Then it has a point at 4, 2, and that's just because the square root of 4 is 2. So I know that's what my original parent function looks like. So this guy's going to have the same kind of step pattern. It's going to go down 1, over 1, and then it's going to go over 4, 1, 2, 3, 4, up 2, because there's no stretch. So it's going to have the same kind of points, just facing a different direction and starting in a different spot. So that's my transformed function. And you should always label stuff on your graph if you're plotting more than one function on the same grid. Okay, moving on to the, I don't know, you can call this a rational or reciprocal function. You should know the names of them. So this is a reciprocal function, or rational, you can call it. So I know this 2 up top is my a value. So that's going to be a vertical stretch of 2. And down here, there's no plus or minus beside the x, so I have no left or right shift. And this +1 is going to shift my graph up 1. Okay, so for this guy, I like to plot my asymptotes first. So I know this up 1, this +1 thing is going to move my horizontal asymptote up 1. So I'm going to have an asymptote at y = 1. So that affects your horizontal asymptote. So I'm going to have an asymptote right here. Now my vertical asymptote is affected by my denominator here. And it is always at 0 unless we have a horizontal shift translation, which we don't have. So it's still going to be at 0. So I have 2 asymptotes. And you should be able to write the equations of the asymptotes. So I have y = 1 and I have x = 0. Those are my 2 asymptotes. And that's how they're written, like equations. And then I'm going to plot some points. I'm going to do it in red. So, you know it's going to go, I'm just going to, I have a highlighter, but anyway, it's going to be something like this. It doesn't have to be the most accurate graph in the world, but if you want to get maybe, there's not going to be a y-intercept, but so if you want to try to find maybe the x-intercept, you could. I don't know how you feel about that, but here's how you could find the x-intercept. You could sub 0 for y. So you got 2 over x plus 1. I'm going to move my 1 to the other side. So it'll be -1 = 2 over x. And then I'm just going to like cross multiply. So I have -1 x = 2. Or I'm multiplying both sides by x, really is what I'm doing. So I know x = -2. So I don't know. If you want to find an x or y intercept, you're just subbing 0 into a variable. So now I know I've got, oh yeah, I was going to use red, an x-intercept at -2. So that might just help me get a little bit of a more accurate graph. I also know I have a vertical shift of 2. So like normally your graph starts kind of, I like to picture it like 1 away from the asymptote, like over 1, up 1 away. But now it's going to make it shift vertically faster. So I'm going to have like over 1, up 2 kind of away from my asymptotes. So I know I'm going to have a point there. No, we didn't go over that too much, but if you understand that, you could put that point in as well. So yeah, it would look kind of like that. The vertical stretch kind of pulls it away from the asymptote, like from the middle here. So that would be accurate enough. And hey, let's state the domain and range just for practice. So let's state the domain and range of our transformed graphs. So the domain of this red graph here would be x, the smallest x can be is -1. So x has to be greater than or equal to -1, and x is a real number. And the domain, or sorry, and the range. So it looks like the biggest value that y can be is -3. So y is going to be less than or equal to -3, and y is a real number. Just get rid of that. And let's do the domain and range of the rational or reciprocal function. So domain, these guys, I think it's easier to just say that in this case, x can't equal 0 because we have an asymptote there. And x is a real number. It's just easier to say what it can't be for reciprocal. And in this case, y can't equal 1. So it's just at your asymptotes. And y is a real number. And that's it. I only picked 2 graphs. There's like a million more. So yeah, just practice those. Practice makes perfect. Just keep practicing, and you could make up your own equation. Give yourself an A and a K. Like, seriously, if you want to practice these, just be like, okay, I'll do 3 bracket x minus 1 plus 4, and then try to graph it. And then use Desmos to check your work. Open up Desmos. I don't know if you like it, but it's awesome. And then you can actually graph it and see what it looks like and just see if you're right. So if you need a lot of practice with that, pull out Desmos and just practice. Okay, so for practice questions, you can head right into the hub. There's a section called Culminating and Review, and it has like 3 different practice things that you can do. And I'm slowly getting all the answers in there.